Hi everyone, so we're going to look at 26.5 today, Radioactive Decay. So if you've got the book you can have a look, if not you'll just have to take notes from my PowerPoint. Just wanted to begin with a what's the link. So we've got some images there. Can you think about what the link between them is? Okay, the link between them is supposed to be about decay. So you've got the apple decaying, you've got a human, although they're growing, they're actually always decaying into old age. You've then got a decay curve, which you've probably come across in GCSE. You've then got numbers here halving, and there's an infinite number of numbers between 1 and 0, which I always find fascinating. And then you've got here linking this into radioactive decay, which is what we're looking at today. So I want you to be able to state what's meant by the activity of a radioactive isotope, define the half-life of a radioactive isotope, and be able to discuss whether there are any other things that affect radioactive decay. So we're going to talk about half-life. It is a concept you've come across at GCSE before, but we need to talk about it much more specifically at A level, and we need to use specific terms. So when a nucleus of a radioactive isotope emits alpha or beta, it becomes a nucleus of a different element because its proton number changes, and so you get whatever you start with, you end up with a different element. The number of nuclei of the original isotope gradually decreases. So if you start off with 100% isotope X, and during the decay process you're producing isotope Y, the original number of isotope X would gradually decrease from 100% as you change them into nucleus Y. So if you plot this as a graph, it's known as a decay curve. And the rate of decrease of the original isotope gets smaller as the number of radioactive isotopes gets smaller. So that means that at the start you've got lots and lots of X, and so they will decay quicker. More of them will give out radioactivity in a given time period because there's lots of them. As you go through time, there are less and less of X, and so there's less of them to give out radioactivity. So the rate at which they give out radioactivity as a whole is less. So an example of this isn't half-life, but this is just by how you can a mass dropping by a constant factor. So in this case we're using 0.8. So let's say we've got an original isotope of mass m, and it drops by a factor of 0.8 in 1,000 seconds. So if the initial mass is 100 grams, after 1,000 seconds, okay, 0.8 times 100, because you've got 100 grams, yeah, is 80 grams. Okay, so you've only got 80 grams left. After 2,000 seconds, you'd have 64 grams, and after 3,000 seconds, you'd have 51 grams. So initially you dropped by 20 grams, and then you only dropped by 16 grams, okay? And that's because initially there was a bigger mass, and so there was more to lose. Okay, so let's look at that in terms of half-life, which is how we actually describe radioactive decay. You need to know the definition. So the half-life of radioactive isotope is the time it takes the mass of the isotope to decrease to half its initial mass. So let's consider a sample of radioactive isotope X, and it initially contains 100 grams of the isotope, which is what we had in the example before. After one half-life, you will only have half of the original mass, the mass of the original isotope left, okay? So 0.5 times 100 grams, you'd have 50 grams. After two half-lives, okay, you would have 25 grams. And you can see here, the way that you would figure that out is you do 0.5, which is your factor, to the power of how many half-lives, okay, times your original mass, so 25 grams. So the next one, after three half-lives, you can do 0.5 to the power of how many half-lives there are, so that would be 3 times 100, which gives you 12.5 grams. So after n half-lives, not lives, after n half-lives, the mass of the original isotope you have left will be 0.5 to the power n times m0, which is your original mass. Okay. So the mass of the radioactive isotope decreases exponentially. Oh, sorry, my screen recording's just got a little bit funny, so I'm just going to go over this bit again. So the equation for this would then be 0.5, which is the half-life, times n, which is the number of half-lives you've been through, and then m0 is the original mass. Now, the mass of the radioisotope decreases exponentially. So exponentially is like it follows a set pattern, like it halves every so often. Because the decay is a random process. Now, random means you can't tell which one is going to decay at any one time, okay? So it's a random process, and the number of nuclei that decay is proportional, and it's only proportional to the number of nuclei remaining. So it's very much, it cannot be affected by heat, any chemical reaction that's going on, okay? The only thing that determines the rate of decay is how many of that original nuclei are still present. That is it. So if we have a look at activity then, activity of radioactive isotope is the number of nuclei of the isotope that disintegrate per second, i.e. how many bits of radiation is it given out in a second. It's the rate of change of the number of nuclei in the isotope. It's named after a scientist called Becquerel, big B, little q for the unit. So 1 becquerel is 1 disintegration per second, or 1 bit of radiation being given out per second. You get some activities which are really high, so you can get millions of bits of radiation being given out a second, and then you get some bits which are really low, so you can have barely anything given out in a second. Okay, so sometimes you can change this unit of activity to like years, okay, but it wouldn't be in becquerels then. So for a radioactive source of activity A that emits particles or photons of the same energy, you can calculate how much energy you're going to get transferred per second from a radioactive source. Now this is really helpful for things like you can use alpha radiation as a source of energy in a satellite going into space. So you put your alpha radiation in a little container. On the outside of the container there's a metal covering, and then when the charged alpha particles hit the metal covering, it creates a change in the electric field, which then creates a current, and then therefore you have a power source. Ideally, you'd want to know how much energy you're going to get from that power source, because then you can determine what it can run and how many of them you need. So that's easily calculated. You do the activity of your source, which is telling you how many bits of radiation it's giving out per second, times how much energy each of those emitted radiations have, so E. So if you times A by E, you get the total amount of energy being given out per second. And that will allow you then to calculate how much EMF you're going to have, and then therefore the current, etc., etc. So here's an example. For a source that has an activity of 30 megabecquerels, have a look out for this. These units change a lot here, these prefixes, so just keep a look out for them. It emits particles of 2.5 mega electron volts. Look out for this as well, because if you want the energy in joules, you're going to need to convert mega electron volts. So I'm going to calculate how much energy in joules per second we get from this source. So we're going to do A, which is the activity. So I need to convert the mega prefix into a number. So that's 30 times 10 to the 6. And then I need to convert this into joules, so I'm just going to 2.5 mega, so 2.5 mega is 2.5 times 10 to the 6, and then electron volts, so times 1.6 times 10 to the minus 19. So my sum is 30 times 10 to the 6 times 2.5 times 10 to the 6 times 1.6 times 10 to the minus 19. And I get 1.2 times 10 to the... I didn't put the number in. Let me just quickly do it. Typical of me, sorry. 30 times 10 to the 6 times 2.5 times 10 to the 6 times 1.6 times 10 to the minus 19 is 1.2 times 10 to the minus 5 joules per second. Okay. Last bit I wanted to look at this was just, I should go back and just say that joules per second is power. So we're actually working out here is the power of the source. Okay, joules per second is power. So power of the source is A times E. Just want to very quickly look at this graph. We do it in a lot more detail next time, but this is a decay curve graph. So if you have a look here, here is your initial count rate, 80, and if you look on the graph, you always need to check the y-axis to see what's on here because they can have lots of different things on here. So we'll just look initially at the counts per second. So the counts per second are initially 80, okay? Oh, hang on, let me just go back a minute. I just want to use something in here. Yeah, so initially it's 80, and then it begins to decrease. So you have the most number of undecayed isotopes here, and it will decrease, and you should find in a half-life it will be half gone. So we can figure out the half-life from here by going 80 divided by 2 is 40, draw a line across, down, and the half-life is 2, and then check the unit here again because sometimes it's different days. You can check that then by going another 2 days, and it should have halved again, which you can see we go to 4 across to 20. So you can have loads of things on this y-axis. So this is counts per second. Okay. You can also have the corrected count rates. That would be taken off the background radiation. So that would follow pretty much the same thing. It would just be slightly lower because you'd have less counts. You can have activity. Now activity will be much, much higher because when you do a count rate, you're only counting in a specific direction. So the Geiger tube only counts like this way. But if the source is in the middle here, okay, the activity would be all the way around the source. So the activity would be a lot higher, but it would still cover the same curve and it would still have the same half-life. Again, massive original nuclei remaining. It would be completely different to this because obviously mass can be measured in lots of different units. But again, it would have the same half-life. And then number of original nuclei, well, I mean, in a 1 mole of a substance, so let's say 12 grams of carbon, you'd have 6 times 10 to the 23 nuclei of carbon. So that number would be really high. But in all of these, for a single source, they would all have this count rate, this half-life of 2 days. But you must check what's on this line here. Right, what I'd like you to do is have a go at these questions, and next time I will post the answers. Any problems, let me know, okay? If you have the book, it would probably be worth having a look at the next section ahead of time because it is fairly difficult, and if you don't do maths, it introduces logs, which I will help you with. Don't worry if you don't do maths, of course I'll help you with it. But you will probably find it more difficult than others. And of course, when we go back to school, I'll go through it with you as well. Okay, see you. Have a lovely day. Bye-bye.